Hey, welcome. This is the second video on graphing rational functions. In this video, we're going to talk about oblique asymptotes, and we're going to talk about where the function intersects the horizontal asymptote and the oblique asymptote. Okay, a graph will never intersect a vertical asymptote, but it can intersect horizontal and oblique asymptotes. Here's a couple examples of graphs intersecting horizontal asymptotes. You can see the first one intersects twice, and then it goes out to infinity to the right. It gets closer to the asymptote, and then as it goes out to the left to negative infinity, it gets again closer to the asymptote. The one on the right, it does intersect the horizontal asymptote in the middle. It just goes right through it. But the ones on the outside do not intersect the horizontal asymptote. Okay, so what we're going to do is we're going to find where this happens. What is the x value where it intersects the horizontal asymptote? All right, so here's our rational function, p of x over q of x. To find the point or points of intersection of the graph and the horizontal asymptote, number one, well, we need to find the horizontal asymptote. And then we're going to solve for f of x equals k, where k is the y value of the asymptote. So if the horizontal asymptote is y equals 5, you're going to set the function equal to 5. And then these solutions are the x values. Of course, the y value is already the y value that we already have, which is the y value of the asymptote. All right, let's do it. So we're not going to graph this one just yet. We're going to find the intersection of the function and the horizontal asymptote. We're not going to graph it. So first of all, let's find the horizontal asymptote. The degrees are the same, right? The degree of the numerator is 2. The degree of the denominator is also 2. So therefore, it's going to be y equals a over b, where a and b are the leading coefficients. So that would be 3 over 1, which is equal to 3. So that is our horizontal asymptote. Okay, now we're going to set the function equal to 3 and then solve. So you're going to write the function 3x squared minus 3x minus 6 all over x squared plus 8x plus 16 and write that equal to 3. Okay. Now to solve that, it might be a good idea to put a 1 underneath the 3 and then cross multiply. Or you could multiply both sides by the LCD, which is x squared plus 8x plus 16. Either way you get the same result. So cross multiplying, so I'm multiplying 3x squared minus 3x minus 6 times 1, that's on the left, and then 3 times x squared plus 8x plus 16, that's on the right. That's called cross multiplying. Okay, now distribute the 1, which is the same thing, distribute the 3 on the right. And now the cool thing that happens is that the x squareds cancel. Right? So if you subtract 3x squared on both sides, they'll both cancel. So we don't have to worry about that. Now let's just solve what we have left. Bring the 24x to the left, bring the negative 6 to the right. So you should get negative 27x equals 54, then divide by negative 27. And we got our x value, negative 2. So on our graph, at x equals negative 2, the function does intersect the horizontal asymptote. It goes through the horizontal asymptote. That's good to know. So the point of intersection is x equals negative 2. And then what does y equal? Well, we already have it. Y equals 3. So that's where it intersects the horizontal asymptote, -2, 3. Okay, let's go ahead and graph it. Let's see what the heck this thing looks like. So we already know that it intersects. Let's find our asymptotes first. We're going to have to set the denominator equal to 0 and solve to find our vertical asymptote. We know the horizontal is already y equals 3. So if we set the denominator equal to 0 and then factor, you know how to do that already. It's x plus 4 times another x plus 4. So therefore x equals -4. Twice. There's no reason to write it down twice though. So let's graph those two asymptotes, -4, x equals -4, and y equals 3. Now we know from the previous slide that the intersection is at -2, 3. Let's put a little dot there for -2, 3. That's the only place that it intersects. So we just need some points on both sides of the vertical asymptote. Now on the left, if we graph a couple points and they're both above the horizontal asymptote, then we know it's above the horizontal asymptote, and then that's it. Just make your graph there. On the right, we need some points just to the left of that intersection point and to the right of it, because it's either going to come from the bottom, go through it, go above it, above the y asymptote, and then come back down and get close to it. Or it's going to come from the top, go through it, and then go down a little bit and then come back up and get close to the horizontal asymptote. All right, hopefully you kind of understand what I just said. We need some points. So here's some points. I went ahead and just put in from -10 to 5 and wrote some down. Your calculator does it all for you. You don't have to graph all of them. For instance, if you look at the one on the right, -3, 30. I didn't make enough tick marks to get to -3, 30, so I'm just going to kind of show it in that direction. I try to italicize the ones I'm not going to plot. You could also change the scale, so you can do that. You could get the -3, 30, but then it's kind of hard to tell, like we have -0.375, so I don't want to do that. It's your call. All right, so let's plot some of those points. To the left, I'm going to plug in, I have -10, 9, and -9, 10.56. So those are the two on the left. To the right, what did I plot? I plotted the two in red are my x-intercepts. I thought those were kind of cool. So let's plot those, -1, 0, and 2, 0. And what else do we plot? 5, 2/3, so 5 and a little bit up. And 0, -0.375. I didn't put a dot there, but we know that it goes about just underneath the x-axis. And the -3, 30, well, that's way the heck up there, right? It's off my screen. So imagine where -3, 30 is. It's way up there by the x equals -4. So when you draw it, just kind of draw it from coming up from above, hit that intersection point, hit the x-intercepts, kind of go below the x-axis a little bit, and it should look something like that. All right, let's try another. Well, let's talk about another intersection. Okay, here's our next problem. Again, do not graph this one. We'll graph it in a little bit, or we'll graph another. Horizontal asymptote. Well, the denominator is x minus 1 squared. That's the same as x minus 1 times x minus 1, which is, if you multiply it out, x squared minus 2x plus 1. Now it's kind of easier to see what is our horizontal asymptote. The degrees are the same, so it's -2 over 1, which is -2. So that's our horizontal asymptote, y equals -2. Now we'll set the function equal to -2. I'm using the -2x squared minus 3 over x squared minus 2x plus 1. Remember, the great thing about this video is you can always pause and take your time, write it down, go through each step. Put a 1 underneath the -2, then cross multiply. Now distribute the 1, distribute the -2. Again, the -2x squareds will cancel. So I'll add 2 to both sides to get the x by itself. And then divide by 4. So our x value is -1/4. So that's where it intersects the horizontal asymptote. -1/4, comma, -2. It is a little bit of work, I won't lie. Okay, let's go ahead and graph that one. Well, we know the vertical asymptote is x equals 1 if you set the denominator equal to 0. Remember, that's x minus 1 times another x minus 1. So if you set each factor equal to 0, each time you'll get x equals 1. So there's only one vertical asymptote. And the horizontal asymptote, we just talked about it on the previous slide. It's -2. And where does it intersect the horizontal asymptote? At -1/4, -2. So let's go ahead and put a point at -1/4, -2. Kind of about there. Okay, it's just to the left of the y-axis. Now we need some points. So on the part to the left of the vertical asymptote, we just need to know on the left, does it come from the bottom, hit it and go through, or does it come from the top, hit it and go through? So we need some points around it to see what it looks like. So here's to the left. I picked some points, -3, -2, -1, and 0. Plugged it in my calculator. And that's what it looks like. So we could see that, kind of hard to tell without a lot of points, but we could see that as it goes to the left, it's above the horizontal asymptote, and to the right of the point, it goes down below it. So something like that. Okay. Now we need some points to the right, just a couple. All right, there's 3 points. I didn't plot to -11, it's out of the screen. So just the other ones. So that looks like that. It's good enough. Doesn't have to be perfect. Yeah, so we need to know if it intersects, because we need to, like, if we get points above, and if we wouldn't have had the 0, -3, we might not have known that it goes through. So it's kind of important to test if it intersects the horizontal asymptote or not. All right, so just kind of reviewing a little bit. If the degree of the numerator is less than the degree of the denominator, then it's y equals 0 is the horizontal asymptote. And if the degrees are equal, then it's a over b, where a and b are the leading coefficients. Okay, so now we're going to talk about oblique asymptotes, also called slant asymptotes. So if you're looking on YouTube for other videos on asymptotes, the word slant is also used. I use the word oblique. So we're going to talk about the case where the degree of the numerator is exactly 1 more than the degree of the denominator. Okay, so that's called an oblique asymptote. Now, there are asymptotes where the degree is where the degree of the numerator is higher by 2 than the denominator, and that's called a parabolic asymptote. And then there's cubic asymptotes where the degree of the numerator is greater by 3. Anyways, we're not going to talk about those though, not part of this class. So here's some examples where the numerator is greater than the denominator. I should say the degree is greater by 1 for each case. So the first example is x squared and the bottom is x. That's greater by 1 on top. Same thing with the second one. The third one is greater than by 1, but the exponents are different. The exponent is 3 on top and 2 on the bottom. Again, greater by 1. So when we have an oblique asymptote, we do not have a horizontal asymptote. You can only have one or the other. Yeah, just another note, we're not going to cover when it's greater than, where the degree is greater by 2 or 3. That's beyond the scope of this course. Here's some examples of pictures, just little sketches of what we're looking at. We will still have a vertical asymptote, most likely, at least in the examples here. And we will have a oblique asymptote. So that just means it's not vertical and it's not horizontal, it's at an angle. So we need some points, again, on both sides of the vertical asymptote to help us determine where to draw in our sketch. Usually, but not always, usually they are kind of diagonal from each other, across from each other. They can't be above and below because then it won't be a function, but they could both be above the oblique asymptote. That's possible. Right, but we need some points. So the oblique asymptote is going to be of the form y equals ax plus b. In other words, it's just a line where it has a slope that's not 0 or not undefined. All right. How do we find this oblique asymptote? Well, we're going to have to divide. So that's number 1. So we're going to divide the denominator into the numerator. And we've talked about division. You have 2 options. You can either use long division or synthetic division. Well, remember, you can only use synthetic if you're dividing by x plus or minus c. So if you're dividing by, let's say, 2x minus 3, then you cannot use synthetic division. You have to use long division. Now you're going to write the result as y equals ax plus b plus the remainder over x minus c. And what we're concerned with is we're concerned with values as x gets infinitely large or infinitely small. As this occurs, the remainder approaches 0. So therefore, the graph of the function approaches the line y equals ax plus b. This is our oblique asymptotes. What did that just say? What that just said is get rid of the remainder. We don't have to worry about it. So cross it out. Whatever your remainder is, cross it out. Okay, here we go. Let's do it. Find the oblique asymptote of the function. So we're just worried about the oblique. Our process is to divide. Now we can use synthetic division or long division. I think we should use synthetic division here because it's x plus 1. So when you use synthetic, remember to use the opposite of the number on the bottom, or use a number that'll make it 0, so -1. And then 2, 3, 5, it's in order. We don't have to rearrange it. We don't have to add any zeros if it's missing a term. All right, write your line below. Bring your 2 down below the line. Then multiply. -1 times 2 is -2. Add those numbers, that gives you +1. Multiply again. That's -1. Add, that's 4. So we're going to write out the quotient with the remainder. Y equals, so don't forget to write the y equals 2x plus 1 plus 4 over x plus 1. Oh, but what did we say about the remainder? Right, just get rid of it. So this is our oblique asymptote. Y equals 2x plus 1. All right, let's do another one. Find the oblique asymptote. Again, the numerator is greater than the denominator by 1. Oh, but we can't use synthetic. We're going to have to use long division. That's all right. Okay, if you kind of forgot long division, you might want to watch a video on long division, but I'll try to go through it. So we take the first term of the dividend and divide it by the first term of the divisor. That's 8x squared over 2x, which equals 4x. You're going to put that in the x column, so put it above the 22x. And then multiply. So multiply the 4x times the 2x minus 3. That gives you 8x squared minus 12x. Okay, now we subtract. So you're going to draw a line and change the signs. That even rhymed. All right, so we drew a line. The 8x squared is now negative. The negative 12x is now positive. The first column, the 8x squared, will cancel. The second column, negative 22x and positive 12x, that gives us a negative 10x. And then bring down the next term. Now we do it again. First term of the dividend over first term of the divisor. So negative 10x divided by 2x. That equals negative 5. Put that above the constant, so put it above the 17. Now we multiply it again. So multiply negative 5 times 2x minus 3. Draw a line, change the signs. It even rhymed. The 10x column, that cancels. And we get a plus 17 and a minus 15. That's a 2. That's our remainder, but do we care about the remainder? No. So our oblique asymptote is y equals 4x minus 5. So to graph that, we would just pick some numbers for x like 0, 1, and 2. That's a job in itself, plotting that graph. And it's just an asymptote, it's not the real graph. Okay, one thing I wanted to mention is that the graphs can intersect the oblique asymptote. Just like we talked about the horizontal asymptote, the graph can intersect an oblique asymptote. Here's a little picture of one. You could see that in the middle it's going right through it, right? So we'll talk about the procedure. However, if you're in my class, I don't really have any homework problems or exam problems covering the topic. I just wanted to go through the process for you in case you're in another class where that teacher does expect you to know how to find the intersection of a graph and an oblique asymptote. All right, so here's our process. It's very similar to the one we did with horizontal. First, find the oblique asymptote. And then we're going to solve for f of x equals ax plus b. So last time we put the function equaling to the horizontal asymptote. This time we're going to put the function equaling to the oblique asymptote. And if there is a solution, that's the x value. Now, to get the y value, we're going to have to solve for the y value using the solution we found and the equation of the oblique asymptote. So it's kind of another step. All right, let's do it. This one looks ugly. Yeah, I agree. All right, let's find the oblique asymptote. So let's do our division. Of course, we can't use synthetic division. We have to use long division here. So we're going to divide the first term of the dividend by the first term of the divisor. So that's x cubed over x squared, which is x. So that's going to go above the x term in the division. Now multiply that. That gives you x cubed minus 36x. Draw a line, change the signs. Now the x cubes cancel, but we got to bring down the negative 2x squared. And then positive 36x minus x is positive 35x. And then we're going to bring down the minus 1. All right, let's do it again. So now it's going to be negative 2x squared divided by x squared. That'll give us negative 2. Sorry. So negative 2. So now multiplying negative 2 times x squared and negative 2 times negative 36, which is positive 72. Draw a line, change the signs, it even rhymes. The x squareds cancel, and then we have 35x minus 73. And we can't go any further because we have a 35x over x squared. That's not going to give us, we can't divide that. All right, and that's our remainder, but what are we going to do with the remainder? Right, get rid of it. So we now have our oblique asymptote, y equals x minus 2. Wow, that was a lot of work just to find the oblique asymptote. Now we're trying to find out, does it intersect? Does the function intersect? So we're going to set the function equaling to x minus 2. Okay, put a 1 underneath the x minus 2 and then cross multiply. So it's on the right, we're going to have x minus 2 times x squared minus 36. On the left, it's that numerator times 1, which is the same thing. So FOIL on the right, that's x cubed minus x squared minus 36x plus 72. And then we can start canceling out some things. If you subtract x cubed on both sides, those cancel. Oh, the negative 2x squareds also cancel. All right, so now we have negative x minus 1 equals negative 36x plus 72. Do a little algebra to solve that. Bring over the negative 36x to the right, and then add 1 to both sides. So there's our answer, 73 over 35. Not even a nice number, right? That's the x value. How do we find the y value? Well, we got to plug it in. We got to plug it into the oblique asymptote. So using y equals x minus 2, plug in 73 over 35 for x, and then work it out. That gives us 3 over 35. So that's where the graph intersects the oblique asymptote. I know, that was a lot of work. Okay, I'm not going to do any more on oblique asymptotes as far as finding the intersection. I'm going to show you a picture here on the next screen. Here's the graph of the last one we just did. The red line represents the oblique asymptote. And you can see that it does go through it in the middle. That's where it goes, that 73 over, whatever you have, 73 over 53, comma, I can't remember. All right, kind of cool, maybe, maybe not. All right, let's get back to graphing. So this is a general strategy. Not all instructors require the same steps, so just kind of be aware of that. Finding the intersection of an oblique asymptote and the function is somewhat complicated. Therefore, we're not making it part of the strategy here. Again, check with your instructor though. So here are the steps I kind of think are important. Find the vertical asymptotes, number 1. Find the horizontal or oblique asymptote. You can't have both. You can only have one or the other. You should determine if it intersects the horizontal asymptote. Okay. Plot enough points, whatever enough is, and then draw it in. And that's good enough. All right, a couple more examples and then we'll call it a day. Let's see, vertical asymptote. What's our vertical asymptote here? Right, x equals 2. Oblique or horizontal? Oblique, right? The numerator is greater than the denominator by 1. So it's got an oblique asymptote. We could use synthetic division here because it's x minus 2. So when we do our synthetic division, make sure you put a 0 for the x term. All right, so when we divide, it's 2 in front. That's our divisor. That's our value of c. And then 1, 0, 1 inside. Draw our line, bring down the 1. 2 times 1 is 2, add it. 2 times 2 is 4. We don't care about the remainder. So it's y equals x plus 2. Let's graph it. You could either use a slope and the y-intercept if you want. The slope is 1, 1 over 1. The y-intercept is 2. So you go to 2 on the y-axis and then go up 1 over 1, up 1 over 1. Or you can just pick some points. That's what I'll do here. So I picked 0, 1, and 2. For each one, there's the y values. Let's plot those points. And then draw the oblique asymptote. Okay. Now, there's no horizontal, so we don't have to worry about where it intersects, and we're not going to worry about if it intersects this oblique asymptote. I doubt it, but we're not going to do it. I will have problems that, if you're in my class, the problems on my homework will not intersect the oblique asymptote. All right, let's find some points. So here's our function. That's the one we're going to use to get our points. And we want to pick points on both sides of the vertical asymptote. So maybe like -1, 0, and 1. That's to the left of the vertical asymptote. And then 3, 4, and 5. That's to the right. Plug it into your handy-dandy calculator. Plot those points. Yeah, and then it's pretty evident what the graph looks like. All right, here's another one. Vertical asymptote. We set the denominator equal to 0, so 3x minus 2 equals 0, and solve that. You get 2/3. I didn't really show the work. You could do that. Oblique asymptote. Let's see, we can't use synthetic, so we're going to have to use long division. Let's see, 6x squared over 3x, 2x. Multiply. Draw the line, change the signs. Then it's -3x over 3x, which is -1. Draw the line, change the signs. We get a remainder of -7. We don't care. So it's y equals 2x minus 1. Let's make a table. Pick some points for x. Plot those points. Draw in your dashed line. All right, so now we need some points for our function. We're going to pick points on both sides of 2/3. So to the left of 2/3, 0, -1, -2. To the right of 2/3, how about 1, 2, and 3? Plug that into your calculator, get the points. Plot those points. And now you can see where the graph is. Just got to do some connecting the dots. Don't cross the vertical asymptote. How about one more problem? All right, vertical asymptote. None, right? X squared plus 1 equals 0. Nothing. Try to use a square root property. You get a negative underneath the radical. It doesn't factor. You can't use a quadratic formula. Again, use quadratic formula. You get a negative underneath the radical. A is 1, B is 0, and C is 1. Won't work. So no vertical asymptote. That's different. Horizontal asymptote. The degree of the numerator is less than the degree of the denominator. Y equals 0. Let's pick some points. We probably should check to see if it crosses, but you know what? When we pick our points, you're going to see that it crosses anyways. So sometimes if the teacher doesn't say specifically show where it crosses, or sometimes when you're picking your points, you'll see it anyways. All right, but you can make that a step, set that equal to 0 and solve, and you'll get an answer, and you'll see what that answer is. So I picked some points from -4 to 4 and plugged it into my calculator, and that's what I got. So you can see what it looks like. It does go through at 0, 0. So just kind of make a smooth graph, trying to connect the dots. Something like that. Hope it doesn't look too bad. I just drew it in by hand. Anyways, that's it. That was the last one. Hope it wasn't too bad for you. Have a good day.